Okay, so today's lesson is going to be on angular kinematics. So we're going to make relationships between displacement, velocity, and acceleration to their angular analogs. So at first you'll notice that what we have here is we have a circle. At the center there's point O. It's got a radius r, and we have the position A to the position B. So we're moving it through a displacement of A to B. So S represents the arc length and theta represents the angle that we move through. So angular displacement is given by the Greek letter theta, and that represents how far it's traveled. It's often measured in a unit called radians, or rad per short. And the relationship between that theta and its arc length is theta equals the arc length over the radius, where S is defined as that arc length. The other units that you may use are rev, revolution, or maybe even degrees. And this is probably what you're more familiar with. And the unit conversion is 1 revolution, in other words, 1 time fully around, is equal to 360 degrees, so that's nothing new, or 2 pi rad. Okay? So if we have a bike wheel that's got a 0.68 meter diameter wheel and it rotates 28.3 radians, how many revolutions has it gone through? Well, think of this as a unit conversion. We have 28.3 rad, and we're trying to convert it into revolutions. So rads go down below, rev up top, and 1 revolution is 2 pi rad. So what I do in my calculator, I divide by 2 pi, and I get 4.5 revolution. If I want to know how far it traveled, in other words, my arc length, that would be the distance around, well, S is equal to theta times r. Now the only thing you got to be careful of is that theta's got to be in radians. So we're going to do the 28.3 times the radius of 0.68. And that gets me a distance of 19.2 meters. Now angular velocity, is given the symbol, the lowercase omega, it looks like a W, and it's the rate at which an object rotates. And the relationship, just like velocity is a change in position over time, angular velocity is a change in angular displacement over time. And if this has got the symbol of rads, and this is in seconds, then the units are a rad per second. And if we're relating angular velocity and tangential velocity, we have omega, which is, as we said before, is change in theta over time, and theta is S over r. Then if we put these two things together, what we end up getting, if you just kind of plug that in, if omega equals delta over t, over r over t, and this right here, notice this, a displacement over time is rv. So this is really equal to v over r. And then if I cross multiply by r, what I end up getting is v is equal to omega times r. And that's a very important relationship. So the marble to the left has a radius of 1.3 centimeters, and it takes 0.67 seconds to make 1 revolution. What is its angular speed? Well, if 1 rev equals 2 pi rad, then omega is equal to 2 pi rad, that's how far it traveled in radians, divided by 0.67 seconds. And so that gets me a speed of 9.4 rad per second. Well, how fast is it moving forward? That is the tangential speed, okay, v, and that's omega times r. So that is the 9.4 times the radius of 0.013. Okay, we want to... Oh, actually, if we get it in centimeters per second, we could just keep it as 1.3 centimeters. And so I multiplied those two, and I get 12.2, and that is centimeters per second. Another common way of expressing angular speed is to relate it to the frequency. Okay, this is very common in a lot of engineering applications. You might hear of it as revolutions per minute, RPM. Okay, which is given the symbol F for frequency, and it's measured also in maybe revolutions per second. Okay, so that is rev per second. If 1 rev is 2 pi rad, then what we can say is omega is equal to 2 pi times F. And the way we get there, by the way, is that we know that F is equal to 1 over the period. Okay, this is the relationship between frequency and period. And if you basically put in that your period as up here, your period is right there, okay, you get a displacement over a ton. So what is the angular speed of the fan blade based on the strobe light? Well, if we put a strobe light on a everyday fan, what we get is a frequency of 62.5 RPS, revs per second. And so what we really want to do is we want to take that and get it into radians per second. Okay, so omega is equal to 2 pi f. So I take my f, I multiply it by 2 pi, and what I end up getting is 2 pi times 62.5 rev per second. Then that gets me an angular speed of 393 radians per second. And what if its speed if the fan blade is 25 centimeters, so 0.25 meters? Well, the speed, the linear speed, is omega times r. So I take my 393 rads per second, I multiply it by my 0.25 in meters, and I get a linear speed of 98 meters per second, about 200 miles an hour. And that's the outer tip of the fan blade. Now the last quantity that we're going to relate is angular acceleration. Okay, so just like velocity, angular velocity is the rate and change of displacement. Well, angular acceleration is the rate of change in angular velocity. Okay, and it's given the letter lowercase alpha. Okay, so alpha is equal to a change in omega divided by time, which if this is a rad per second, we get a rad per second squared, or if we want to write it in IB units, a rad per second to the minus 2. Now notice that if something is picking up speed, in other words, this disk is starting off slow and getting faster and faster and faster and faster and faster and faster, that not only is the angular acceleration picking up, or not only is the angular velocity picking up, but also the angular acceleration and the tangential acceleration, because this thing is getting faster at any given radius. So what we can have is we want to relate the angular acceleration to the radial acceleration, so the inward acceleration that we've been talking about quite a bit for circular motion. And also, now that something's changing its speed in a circle, then we might want to talk about the tangential acceleration. So that's that value. Okay, so A sub t is the tangential acceleration, and this is your radial acceleration, or along the radius. convert angular acceleration to tangential, okay, well, tangential is the same as saying linear. It's a change in velocity, okay, where velocity is equal to omega times r. So really what we get is acceleration, tangential acceleration, is a change in omega r over t. Okay, and this right here, change in omega over t, is what we called alpha, okay, or angular acceleration. So our tangential acceleration is equal to the, the angular acceleration times the distance, okay, from center. Or rearranging this, alpha is equal to tangential over r. Okay, just rearranging and solving for alpha. But the radial acceleration can be related to angular velocity by the v squared over r. But here v is omega times r, so v squared, what we end up getting is omega squared times r squared over r, and then one r cancels out, and our radial acceleration is omega squared r. And if we combine, if you think of it as two vectors, we have an inward acceleration and we have a tangential, and if you do the overall acceleration, that's be the Pythagorean theorem, then we can then do a squared plus b squared equals c squared, and c being the third side of your triangle. So try out these few more examples, okay? Take a look at the notes above, and if you have any questions, we'll talk about it tomorrow. That's all for now. Thank you. Bye-bye.